Okay, this is another conservation of linear momentum example. This was a problem on the fall 2024 final exam involving calculating the forces on a fluid mixing box. The students did quite a bit worse than I expected, mainly because this problem involves multiple inlets and outlets. So I thought I'd make this video to help you generalize the solution technique for this type of problem. The problem states, consider a steady flow of water at a density of 988 kilograms per cubic meter in a fluid mixing box with two inlets. So at point 1 and 2, the fluid comes in, and one outlet at point 3. The weight of the water in the box and the box itself is 4,500 newtons, and the gauge pressures at the inlet are 4 kPa at point 1 and 2.5 kPa at point 2. The outlet discharges at point 3 to atmosphere as a free jet, so at 100 kPa. There are several other parameters given in the diagram that you'll also need. The inflow at point 1 on top of the box enters at an angle of 60 degrees at a velocity of 2.5 meters per second and a volume flow rate of 0.75 cubic meters per second. At point 2, on the side of the box, the water enters at 1.8 meters per second and a volume flow rate of 0.45 cubic meters per second. And at point 3, the water exits as a free jet at an angle of 55 degrees and a velocity of 3 meters per second. You're asked to calculate the volume flow rate at point 3 in part A, and in part B, you're asked to calculate the reaction forces in the X and Y directions required to hold the box stationary. These are the combined forces at the flanges and the mounting brackets required to hold the box in place. Oh, by the way, I should mention that you can download the PDF of this solution at the course website. There's a link in the video description. Okay, now we move on to the solution. First, in part A, we solve for the volume flow rate at the outlet. Of course, we'll need that flow rate for the force calculations in part B. Here I've shown the mixing box and the control volume in red. Conservation of mass, in other words, continuity, requires that the mass flow rate into the control volume is equal to the mass flow rate out of the control volume because there's no mass storage. We have two inlets at 1 and 2 and one outlet at 3. So m.1 plus m.2 must equal m.3. Recall that mass flow rate is equal to density times volume flow rate, so we can express this as rho Q1 plus rho Q2 must equal rho Q3. In this problem, the fluid is water, which is incompressible, so density is a constant, which we can cancel in all the terms. So rearranging, we get that Q3, the exit flow rate, is the sum of the inlet flow rates, Q1 plus Q2. As a side note, you should recognize that for the current problem, this would be true for either steady or unsteady flow because the fluid is incompressible. The mass flow rate in must equal the mass flow rate out since there can't be any mass storage of an incompressible fluid inside a control volume of fixed size. Okay, so we can just substitute the values. You're given in the problem statement that the volume flow rate at 1 at the inlet is 0.75 cubic meters per second. At the other inlet, 2, the volume flow rate is 0.45 cubic meters per second. So we add these up and we get that the volume flow rate at the outlet is 1.2 cubic meters per second, which is the answer to part A, which we'll need for part B. Moving on to solve for the reaction forces required to hold the box stationary. The first step is to draw a free body diagram with all the forces on it, as I've shown over here. So we have the unknown reaction forces, Rx and Ry, that we want to solve for. We have the weight of the water in the box, W, and we have the pressure forces at the inlets and the outlet. Note that the pressure forces act inward and normal to the control volume. This has nothing to do with the flow direction, by the way. Note also that all the pressures must be expressed as gauge pressures in these types of problems. This allows you to avoid calculating the pressure forces on the outside of the box. If you work in gauge pressures, the pressure on the outer surface is zero because it is at local atmospheric pressure. If you don't understand this, hold on until the end of this presentation. I'll show you what happens if you use absolute pressures, and it's a total disaster. Okay, so moving on. Next, we apply conservation of linear momentum. The sum of all the forces on the control volume equals the rate of change of fluid momentum. So m dot v summed over all the outlets minus m dot v summed over all the inlets to the control volume. In the current problem, we only have one outlet and we have two inlets. So this becomes m dot 3 v3 minus the sum of m dot 1 v1 plus m dot 2 v2. For example, this is how a jet engine works. A jet engine takes in air at low momentum and pushes it out at very high momentum to produce thrust. Okay, so I've rewritten the conservation of momentum equation at the top of the page here. Notice that the f and v variables here are bolded. So this is a vector equation. In 2 dimensions, this is actually 2 equations. So the total force F has components Fx and Fy in the x and y directions. Similarly, the velocity vectors have velocity components in the x and y directions. And by the way, the mass flow rates here are scalar quantities. So what we do is consider this equation one direction at a time. And here I'm starting with the x direction, and I'm taking x as positive to the right. So we get that the sum of the forces in the x direction, so sigma Fx, equals the rate of change of fluid momentum in the x direction. So now the momentum terms only involve the x component of the velocity vector, which is u. So we have the rate of x momentum out minus the rate of x momentum in. Okay, so now what we're going to do is consider the sum of the forces. So looking at our free body diagram, we have Rx in the positive x direction, so plus Rx. P1A1 has a component in the positive x direction, and its component is P1A1 cos theta 1, and that's a positive because it's in the positive x direction. P2A2 acts purely in the negative x direction, so it's minus P2A2. And notice here that there is no pressure force at the outlet. This is because the water discharges to atmosphere at point 3. And so the common assumption here is that at this location you have 0 gauge pressure, so no pressure force. Next, what we can do is express these 3 x components of velocity in terms of the velocity components we're given in the problem statement. So starting with U3 equals V3 cos theta 3, but negative because it acts in the negative x direction. Similarly, U2 here is V1 cos theta 1, but this is in the positive x direction, so plus V1 cos theta 1, and V2 acts entirely in the negative x direction with no y component, so U2 equals minus V2. So now making the substitutions here for U1, U2, and U3, we get that the sum of the forces in the x direction equals m dot minus V3 cos theta 3 minus the sum of the momentum entering in the x direction, which is m dot 1 v1 cos theta 1 plus m dot 2 minus v2. At this point, we can solve for the unknown reaction force in the x direction, and that's what I've done here. Feel free to check my algebra, of course. Okay, at this point, I always recommend that you do a bit of a sanity check. Make sure that the force directions make sense. So Rx is the force in the x direction. If P1 increased, it has a component in the x direction, so it would tend to reduce Rx. So it makes sense that that's a negative sign. P2A2 acts in the negative x direction. If it increased, it would increase Rx. So that makes sense that that's a positive sign. The momentum terms here are a little more complex, but think of that jet engine problem. M3 V3 cos theta 3 is the x momentum of the fluid being ejected at the exit. Just like a jet, it would produce a force in the x direction. So that would tend to reduce Rx. The fluid coming in at 1 would tend to also reduce Rx, so it makes sense that it's negative. And if you had a higher velocity of flow coming in at 2, it makes sense that it would tend to increase Rx. So that is a positive sign, which makes sense. So our signs look okay, and we can move on and look at substituting some values. So once again, I've rewritten the equation that we just derived for the X reaction force. So what we need to do now in order to substitute all the values, there's still a few variables we don't know. We don't know A1, we don't know A2, and we don't know the three mass flow rates, m.1, m.2, and m.3. But you'll see that these can be calculated fairly easily. Noting that Q equals VA, so the volume flow rate is the area times the velocity, we can get the area at 1 is Q1 divided by V1. And you'll notice over here what I've done is I've listed all the values given in the problem statement. So A1 is 0.75 cubic meters per second divided by 2.5 meters per second, which works out to 0.3 meters squared. Similarly, A2 is Q2 divided by V2, so 0.45 cubic meters per second divided by 1.8 meters per second, which works out to 0.25 meters squared. It's a simple matter to calculate the mass flow rates, m.1, m.2, and m.3, noting, as we did previously, that the mass flow rate is the density times the volume flow rate. We're given in the problem statement that water has a density of 998 kilograms per cubic meter. So 998 times Q1 gives the mass flow rate at 1 as 748.5 kilograms per second. Similarly, the mass flow rate at 2 is rho 2 times Q2. And you can see here Q2 was given in the problem statement as 0.45 cubic meters per second. So we get 449.1 kilograms per second. And M3 we can calculate using the volume flow rate that we calculated in part A, which was 1.2 cubic meters per second, times the density of water gives 1,198 kilograms per second for M3. Now we can move on and make the substitutions. Again, I've reproduced the equation here. So making the substitution for the first term, which is minus P1A1 cos theta 1. So P1 is 4 kPa. Again, I've reproduced the values from the problem statement in the diagram here and the values that we just calculated for the areas and the mass flow rate. So that's going to be 4,000 newtons per meter squared times A1, which is 0.3 square meters times the cos of theta 1, cos of 60 degrees. So that's correct. Next, we do P2A2. P2 is 2,500 newtons per meter squared times the area that we just calculated as 0.25 square meters. So that term is correct. The next term is the m.3 V3 cos theta 3. So there's m.3, 1,198 kilograms per second. V3 is 3 meters per second, and the cos of theta 3, which is 55 degrees. You'll notice the units all work out. These are all have units of newtons, and so this is kilogram meter per second squared, which is a newton as well. For the next term, that's m.1 V1 cos theta 1, which is 60 degrees, and the last term is m.2 V2. So 449.1 kilograms per second times 1.8 meters per second. And if you do the math on this, you can check my arithmetic here, you get minus 2,160 newtons. And the negative sign means that Rx is actually in the opposite direction. So it should be written as Rx equals 2,160 newtons to the left. And that's the answer for the reaction force in the x direction. So now we can move on and do exactly the same thing, but in the y direction. So we're considering the sum of the forces in the y direction, so just Fy and just the y component of the velocity vectors. So you get that the sum of the forces in the y direction equals m dot 3 times the y component of the velocity vector at the outlet minus m dot 1, the y component of velocity at one of the inlets, and m dot 2, which is the other inlet, times the y component of velocity at that inlet. So considering the sum of the forces in the y direction, we have Ry in the positive y direction. W here, which is the weight of the box and the water in the box, acts in the negative y direction, so it's minus W. Similarly, the pressure force here at P1 has a negative y component, so it's minus P1A1 sine theta 1. And you'll notice there's no pressure force in the y direction at 2 because it acts in purely in the negative x direction. And as we discussed previously, the gauge pressure at the outlet is 0, so the outlet has no component of pressure force in the y direction. Next, we can move on and express the y components of velocity here, v1, v2, and v3, in terms of capital V's, in terms of the velocity vectors that were given in the problem statement. So as we did before, so lowercase v3 equals uppercase v3 sine theta, because we want the vertical component, but it's negative because it acts in the negative y direction. Similarly, lowercase v1 is capital V1 sine 60 degrees, again, negative because it acts in the negative y direction. And at location 2, v2 is purely in the x direction. There's no y component, so lowercase v2, the y component of the velocity at inlet 2 is 0. So making these substitutions, we get that the sum of the forces in the y direction equals m dot 3 minus v3 sine theta 3 minus m dot 1 and then minus v1 sine theta 1. That looks correct. Now what we can do again is solve for our y here, and that's what I've done next. You can check my algebra. I'm pretty sure it's correct. Again, we want to check that the force directions make sense before we substitute values. So Ry is in the positive y direction. You could imagine if this box got heavier, it would increase Ry, so it makes sense that that's positive. Similarly, if the pressure here increased, it would increase Ry, so that positive sign makes sense. In terms of the momentum flux terms here, this m dot 3 v3 term is the momentum leaving the control volume, which would produce a thrust that would act to lower Ry, so it makes sense that that's a negative. And the incoming momentum here would act to increase Ry. Makes sense, so that's a positive. So the directions of the terms make sense. We can move on and make some substitutions. So once again, I've rewritten the expression up here that we had on the previous page, and we can just make the substitutions. We know all the variables now. So the weight in the problem statement you're given is 4,500 newtons, and then P1A1 sine theta. So P1 is 4,000 newtons per square meter times 0.3 meters squared, which we calculated previously, times the sine of theta 1, so sine of 60 degrees, that's correct. Then minus m dot 3 v3 sine theta 3. M dot 3 is 1,198 times v3, 3 meters per second, times the sine of theta 3. And that term is negative, so that's correct. And then plus m dot 1 v1 sine theta 1. And there's the mass flow rate that we previously calculated at 1, the velocity at 1, 2.5 meters per second, and the sine of theta 1, 60 degrees. And if you do the math, that gives that the reaction force in the y direction is 4,220 newtons upward. So that's the answer to the y reaction force. Okay, I said I'd talk about why you have to use gauge pressure in these types of problems. So here I've shown our free body diagram using the gauge pressures, which is of course the correct approach. The key point to recognize is that this trick of using gauge pressures allows you to avoid calculating the pressure forces on the outside of the box. If you work in gauge pressures, the pressure forces on the outer surfaces are zero because the outer surface is at local atmospheric pressure. But consider the alternative. Imagine using absolute pressures. So at the inlet here we have P1 plus the atmospheric pressure, which is the absolute pressure. Here we have P2 plus the atmospheric pressure, and at P3 we just have the atmospheric pressure. So far so good. But now we have to include the atmospheric pressure on the outside of the box, which looks something like this. So I hope you can see that this becomes an integration nightmare. It's possible, of course, but it becomes extremely difficult to get the correct pressure forces if you work in absolute pressures. So by now, you should have noticed that the atmospheric pressure given in the problem statement, that 100 kPa, was a red herring. You don't need it. You only need the gauge pressures. And that completes this presentation.